report works. So kia ora, as I said, welcome to the Complexity and Tractability webinar with Tim. Tim, thank you once again for sharing your whakaaro and helping us out. I'm going to hand it over to you and I'm going to mute myself. Kia ora tātou.
Right. Well, yeah, kia ora tātou. Good to see familiar faces and a couple of not so familiar faces, and I guess a few people might be watching later on as well. So complexity and tractability. When I was first working with primary school kids, one kid said to me, "Why do you use such big words for such simple ideas?" And I think complexity and tractability have to be one of those big words for simple ideas things. So hopefully we can sort of break them down into things that aren't too scary. I'm aware that there are people in the room who have probably taught this several times and others who may never have seen it. It's 3 credits, so in theory, your students are going to spend 30 hours on this. I'm going to compress that into less than well under 1 hour. Well, I'm doing my best. And one of the problems with this standard is it did get caught out by the change in standards because there was an algorithms standard at level 2. Was it? No, it was even level 1, I think. Yeah, level 1. And so students would then have that background for then doing complexity and tractability. But of course, that got lost. It was going to move to level 2, and then level 2 never happened, which means that it is kind of a bigger standard, but it is one that like there's more big words for simple ideas in it. But I think it's one which is very well packaged, very lots of material, lots of exciting things to do in it. So it's not too airy-fairy. You can really get your teeth into things in it. And so I think it's one that's well worth considering working with on your kids. And maybe I'll convince you too that it's useful for them. So, as for my other webinars, I've got hopefully this is the right link I've put in. It's always scary when you put in some random characters and hope that it goes somewhere useful. So this is a document which at the moment, I've just put a few links in. You should be able to put comments in it or suggestions, which is great. I'll look at it afterwards. If there are questions there that I didn't, like, can you put a link here to such and such? I'll do that afterwards. And so it's sort of a bit of a collecting point for ideas. Thank you, Tracy. So it's in the chat now. I'll move on. So yeah, this is a level 3 achievement standard. It's external, which means it's more or less an exam format. Well, in fact, it is. Here we go. It's called an exam. Analyze an area of computer science. You've got a choice of 3 areas, and one of them is complexity and tractability. And in the assessment specs, it says it's got all these big words that polynomial, non-polynomial, big O notation, P, NP complete, algorithms, heuristics, and so on. So they're all the big words that hopefully, after your students have spent their 30 allegedly hours on it, or at least perhaps 10 or 20 hours on it, will be able to just use to answer questions, to discuss things, and so on. So the big thing here, and the reason I think this is such an important topic, and basically every computer science department around the world, this is one of their first topics that they have. Every computer science student does this after they've learned to program, is to make sure that your computer programs aren't carrying out tasks the hard way. And because if they are, they're wasting resources. And so the hard way means, doing instructions they don't need to do, taking longer than they need to. And many of you are probably aware the hard way can be ridiculously hard, that if you do it the really wrong way, it could take millions of years for it to finish. But we're also interested in things that take 2 minutes when they could have taken 1/10 of a second, because the time is important to the user, most important part of the system, the person using it. Why make them wait 2 minutes when someone else can do the same thing in less than a second? Computer storage is really important because that's the cost of the device that they're using. Otherwise, you wipe out their device. And power is really important. If it's a mobile device and the battery goes flat, they're not going to thank you. And if it's a big data warehouse and it has to use twice as much power off the grid than it would otherwise, then by using the wrong algorithms, then that is just a waste of resources and literally heating the atmosphere as well. I think the other cool thing about this is that there's a bunch of unexpected things that if you ask someone in the street or maybe the kids coming into your class that they might not have thought of. So one of the big things is that the amount of time that a program or an algorithm takes is it's unusual for it to increase linearly. Now you would think, we're talking about things like when you click on sort by date or sort by file size in the Finder, in the operating system, you would think that if it was twice as big, it would take twice as long. That is almost never the case. And in fact, for some problems, no matter how big the input is, we can deal with them really, really quickly. Searching billions of items can be done in a fraction of a second. Even if you get tens of billions of items, it's still probably a fraction of a second. Other times, really small inputs take a really long time. It can blow out on things. And in fact, sometimes a small input can take an impossible amount of time. And by impossible, we mean centuries or millennia, um, which is sometimes good. If it's a security attack, you want it to take centuries before it comes up with the right attack on your security. You don't care if someone breaks your security in 100 years' time. Um, and then the other surprise is there are some things that you would think there was an algorithm for, but there is none. And we can prove that nobody will ever write or design an algorithm for it. That's sort of getting right into the excellence and kind of mind-boggling sort of territory. But I think it helps students to realize that computers aren't quite as smart as they might think they are. Um, so another key idea that I think is really important for students to get straight in their heads is that we're talking about problems and algorithms that solve those problems. Now, the word problem in this context is things like sorting a list into order, finding a value. Someone's swiped their credit card. The system needs to look up their credit card in a database and tell you what the bank balance is to make sure they've got enough money to pay for something. It could be optimizing the loading of a vehicle or something like that. So we've got these problems that are kind of can be defined mathematically or very logically. And then we have algorithms that will solve them. And often there are many algorithms that will do exactly the same solution. So if I say sort these numbers into order, 3, 1, and 2, the answer is always 1, 2, 3. But there's literally dozens and dozens of ways, dozens of algorithms that can do that. And we will spend a bit of time looking at sorting. So we'll come across one called quicksort, another called selection sort, and then there's pages of them if you look them up on Wikipedia. For your students, for most of the time, we only look at about 4 or 5 different problems, and enough for them to get an idea of the range of problems there are, and typically only look at 2 algorithms for each problem. It doesn't mean that there are 2 known algorithms. There are usually lots and lots of algorithms, but perhaps 2 that have really interesting properties. One that's sort of not great and one that's really good is what we're typically going to do with those. But it's really important to distinguish the problem from the algorithm. Okay. And here are some of the big words that are going to come up. I'm going to skip over this, but just for the record, your students really need to be comfortable with this. So algorithms, what are they? The Computer Science Unplugged material has a lot of stuff on algorithms because algorithms exist without computers. Okay, in fact, even many of the algorithms we use today, people knew before computers had been invented, because the algorithm is the idea of how to do something, and then you convert that to a program that actually does it. And we call it them computational algorithms because they only require steps that a computer can do. So, for example, the girl in this picture here is doing computation. She's using a pair of scales to sort these weights into order. So she can't see how heavy they are because they all look the same, but they're not the same. The command on a computer for comparing 2 values to see which one is larger is typically the if command, if A is greater than B. But we've simulated this off the computer using a pair of scales that can only compare 2 values at a time. So the only rule that we tell the kids is you can only compare 2 weights against each other at a time. In other words, you can only do an if statement, and you can do things over and over. In other words, you can have loops. And basically, that's all a computer can do anyway, is comparisons, loops, and, well, following sequences of instructions. And as long as you limit yourself to that, then you're basically doing a computational algorithm. So the problems, some of the main problems that we're going to look at, searching, which is like obviously things like a search engine, type something into Google, it looks for all the pages that have got that word on it, or you just search on your computer, find all the documents that contain this word or something like that. So you're given what's called a key, a word that you're looking for or a number that you're looking for, and the data that it's going to look through. That's a completely solved problem. We know lots of ways of doing that. For example, there's a thing called binary search that we'll look at in a minute. By the way, the best way for searching is usually called hashing, but there's no particular need for your students to do that, although it's kind of a fun thing to do. In fact, if they were doing security, hashing comes up there as well, so it's kind of nice to use it for both. Sorting, which I've talked about, putting things into alphabetical order, sort files by name, sort files by date, and that sort of thing. That's solved. There's an algorithm called quicksort and another one called merge sort that pretty much the way that most computers are going to use. And by the way, this also means that because most computers use them, nobody's going to end up writing these algorithms. So someone will probably tell you pretty soon, look, I can just download these algorithms. Why do I need to know how they work? And the reason is so you can choose the right algorithm at the right time. Quicksort is a fantastic algorithm, but there is one circumstance where it works really slowly. And the weird thing is actually one of the places it can work really slowly is if you give it a list that's already sorted. It freaks out on a sorted list and goes really slow. Right, another problem we'll look at, traveling salesperson problem, having to drop off lots, a courier van or something like that, dropping off lots of parcels. What's the shortest route to drop off, say, 20 parcels? Nobody knows the fastest way of doing that. It's just, we've been searching for decades to find good algorithms. Nobody has found one that will finish in a reasonable amount of time. And so then we have to work out how do we deal with that. And basically we make do with algorithms that are almost correct. Probably not the best way. We're probably wasting some petrol or fuel dropping off parcels, but we've got to get them dropped off. We're not going to let the computer think about it for a year or two. And then there's problems like tiling and a couple of others where we know, now tiling is where you've got tiles with patterns on and you need to do a tile where the patterns all match up. We can prove that no computer for particular types of tiles will ever be able to answer some questions about, finding large patterns of tiles and so on. You'd think it would be possible, but it just cannot be done. Right. So I'll just start with searching as an example. There's lots of ways of doing it. We've done it with ping pong balls under cups, which is a very physical way of doing it. So you have ping pong balls with numbers on hidden under cups. There's a video on Unplugged of these two characters doing it. And the student can only lift one cup at a time and look at the value on a ping pong ball, and they have to find a particular one. We've got things like, it's a bit like battleships or hidden loot. There's the video on the field guide. This is Caitlin Duncan. She wrote most of that chapter, and she did a video searching for books in a library that illustrates some of the different algorithms you could look. Basically, she's got someone doing a linear search going through every single book in the library until they find the one that they want and start to realize how bad that algorithm is. And we can also work with phone books. So quite often I start off by thinking about searching, and this is a problem that can be done surprisingly fast. So and phone books are good, although they're kind of going a bit out of fashion, and students are maybe not that familiar, but if you can find an old phone book and get them to search them, it's a real physical way of understanding this. And the algorithm we would use is turn to the middle page. So you give them a name they have to find, Smith or whatever you want. But the rule is turn to the middle page, and does the name come before or after that? Does Smith come before or after that middle page in the alphabet? And then they choose which half it's in. And for that half, does it become before or after that page? And so each time they're dividing the number of pages in half. So if there was 512 pages in a phone book, the first page they look at, they'll end up with 256 pages to deal with. And then they go to the middle of that, they'll end up with 128, then 64, 30, and they can work out those numbers. But if you count that, and by the way, I literally ripped the phone book in half, which is sort of memorable for them. But so I'm measuring this. I'd have to rip it in half 9 times, and I'll be down to the one page that name is on. So 512 pages takes 9 of these rips. Okay, is that making sense so far? Okay, just throw a question in if I'm sort of, as I said, I've got 30 hours of stuff to cover in 1 hour. Now, what the question I asked the students is, what if the phone book was twice as big? And they'd go, well, instead of 9 rips, it'll take 18. And then they go, hang on a minute, I know that look in your item. And they think about it and go, look, if there's 1,024 pages, you look at the middle page, rip it in half, and you've only got 512 pages. So it only adds one more step to the algorithm, to the process. And of course, with the phone book, it's computational because all you're doing is you're getting them to compare a name with the name in the middle, and you're getting them to work out where halfway is. Computers are good at working out where halfway is. So twice as many pages, only one more step instead of nine. And then think of a big thing like Wikipedia. Someone printed Wikipedia, and it's that fat. It's 5,000 pages, I think. You'd only need to look at 13 pages to search all of those 5,000 pages. And you imagine if you printed all of Wikipedia, 1 million pages, if you work it out, it only takes 20, you only have to look at 20 pages or rip it in half 20 times. And if your students don't believe that, then you just go, well, 1 million, the first time, it'll be 500,000, then 250,000, 250,000, then 125,000. And pretty soon you're down to 1,000. And then before you know it, you're down to one. This is remarkably good. In fact, I usually get them to work out for 1 billion pages, which, by the way, would stretch from Christchurch to Oxford, the, the local Oxford. Huge book, but theoretically, you only need to look at 30 pages of it to find a particular thing in it to search for a value. And in fact, at that point, you can say, well, where does someone search 1 billion items and only do 30 steps in an algorithm? And then they realize, oh, search engine can search 1 billion items, or even if it was 1 million items, then you're talking about 40, in total. That would actually stretch pretty much halfway around the world. And yet you would only need, apart from the practicalities of going from one end of the book to the other, you'd only need to look at 40 pages to find a particular one. So 40 steps, remarkably fast. Now, mathematically, that function is called a logarithm. And this can freak students out. They probably haven't covered logarithms in maths, or if they have, they probably chose to ignore it. It's also really confusing because the word logarithm sounds like algorithm, and yet they are completely unrelated. They come from different languages and all sorts of things. But a logarithm just means how many times you can halve a number until you get down to one thing. Right? So the logarithm of 4 would be 2. You halve 4 to get to 2, and then halve 2, you get to 1. So twice you can halve it. Won't go into a lot of detail, but it's well worth them getting stuck into this, trying out some logarithms. We call it log to the base 2 because it's halving each time. Calculators often do log to the base 10. How many times can you divide something into 10 until you get down to one item, which is not quite so helpful. But have them play around with them. The logarithm is one of the most useful things in algorithms, because if your program or your algorithm takes logarithmic time, log n time, then nobody can ever give it a big input that will take many operations. Even if you had every grain of sand in the world to process for some reason, the logarithm of that is still just a small number that you could process by hand. So logarithms are our friend. So exercises students could do to get face-to-face with this, do those estimates for a phone book, and then think about, what if you're doing unsorted? What if I told you to find this particular phone number? Then they can't use that binary search algorithm. Binary search is about dividing it in half and half again. That's the binary. They'd have to use a linear search algorithm, which is start at the beginning and go through the whole thing. And suddenly, that is quite different. That is not logarithmic. If the phone book is twice as big, it will probably take twice as long to go through every page of the phone book and so on. And now we have another algorithm, achieves the same thing, a linear search, but it is linear. That's how it gets its name from. It's proportional to the amount of things that are being searched. As I mentioned, ping pong balls hidden under cups is a nice physical way of doing it. And on the field guide, we have boxes that students can click on. In fact, I think I've got them up here. Oops, hang on a minute. Here's Caitlin. By the way, Caitlin had a baby a couple of weeks ago. That's pretty cool. Yeah, just mention that, since a few of you have met her. So searching out them. So yeah, here we go. So there are 9 boxes, but you're only allowed 5 guesses, and you have to find the number 319. And so, students might start off going, oh, let's look at the first one. And then they realize, oh, hang on, this isn't going to work. And you can have a little argument start in the class. But pretty quickly, if I just restart that, if I click on they'll reason for themselves. You should look at the middle, and we're looking for 455, so it must be over here on the right-hand side. And I found it in 3 clicks because I was using a binary search, and it gets bigger and bigger. And in fact, here we've got 25 boxes. And again, if there are 1,000 boxes, they'd go, well, that's ridiculous. And then you think, oh no, 1,000 boxes, you only need to click on 10 of them to find what you're looking for. So ways for them to experience firsthand what a logarithm is, logarithmic responses. Right. Now I'm going to do a completely different algorithm. Again, probably much faster than I'd like to, but many of you may have done this. And this is just sorry. Get back to it. So it's what I do is I say, well, we've got some high scores from a game, and behind each of these boxes is a score, and I'd like you to tell me the largest one. So click on the first one, it's 744, 821, 7, and so just going through that, that's the only instructions, but they will in their head be keeping track probably of the largest one so far. And then you can discuss with them in detail, what algorithm did you use? And they'll start with probably something quite vague like, oh, I just kept track of the biggest one. But literally, what did you do? When I clicked on 799, and you want them to be able to articulate that they compared it with the biggest one so far. Comparison, if statements, computers are good at that. They're very simple to do. And so they kept on doing these if statements, and if it was bigger, then remember the bigger number. And here there are 11 boxes, and the question is, how many comparisons did you do? It's a trick question because it's 10 comparisons. The first one didn't get compared with anything. And this is what they're doing here is what's called analysis of the algorithm. They've got an algorithm, they've articulated it, and their particular algorithm, they are analyzing it. And analyze just means work out how much work is involved in doing that algorithm. In the standard, it's sometimes called the cost of the algorithm, or the amount of time it would take, or the amount of steps. We often measure it in terms of the number of comparisons you make, mainly because most algorithms doing comparisons, that will be a critical step that dictates how fast it is. And so you're getting them used to the idea of counting comparisons. And that was so 11 boxes would take 10 comparisons. What about 100 boxes? And they'll hopefully quickly get to the point, oh, that would take 99 comparisons. What about 1,000 boxes? Oh, 999. And so they're doing the analysis. And then the general case of analysis, we say there are n boxes. And in algorithms, almost always n is the number of things that are being searched or sorted, or in this case, finding that this is not searching, this is finding the largest number or maximum value. But we have n values, and the correct answer is, of course, there are n minus 1 comparisons that will be made. Now, that algorithm basically, if I had 1,000,001 boxes, it will take 1,000,000 comparisons. So every time the number of boxes doubles, it will take roughly twice as long, give or take a little bit. And by the way, that give or take a little bit, that's one. It's like, oh, this is going to cost $1,000,000. And you go, oh, no, actually, it's 999,999. Who cares, right? That's 1 out of 1,000,000. 1,000,000 is a rough guide to how long it takes. And that's where the big O notation comes in. We'll get to that in a minute, but it comes up pretty quickly because computer scientists use it a lot to go, look, it is n minus 1, but let's not write the whole thing out. It's roughly n. That's if you're dealing with 1,000,000 things, n will do the job. So we say that it's order n, or and I'll show you the notation in a minute. You've probably seen it, big O with n in brackets. And so again, it's a chance to introduce that notation. Now, part of the reason for doing this algorithm for finding the maximum is that it's also, oh, so there's the analysis there. It's also useful for leading into sorting. And so the first thing is that the two problems that we talk about a lot with teaching about algorithms is searching and sorting. Partly because they are really useful. Almost everything you do, every time you touch a computer, the first thing you'll probably do is search, whether you're in Microsoft Word searching for something, you're looking through your files, looking for something or whatever. But the other thing that happens an awful lot is sorting. However, that's not the reason we really use it here. The reason we use it is that it illustrates all the big issues in algorithms very nicely. All the stuff I've been talking about, you can give them illustrations of using searching and sorting. If they ever had to implement searching and sorting, chances are they can just download the algorithm of their choice. They know that it's been analyzed. They know whether it's a good algorithm or not based on its analysis and its big O notation. And so they won't ever have to do that, but they understand what they're building into their programs, into their big system that hopefully thousands of people are using that may or may not make it go fast. Big numbers will come up a lot, by the way. Again, computer scientists generally aren't interested in sorting 10 values or 100 values. We worry about it when you've got 1 million customers or 100 million data items, 100 million transactions or something like that. That's when things really, really matter. That's where one wrong move and it could take, 2 minutes or even 2 hours to look up something as opposed to a fraction of a second. And that fraction of a second, if it's someone using a computer live, is really important. So HCI, that is a level 1 standard. Hopefully they know from that you've got 0.1 of a second to please the user for them to feel like it's fast software. Or if it's a really good thing that you're doing, they'll probably give you 1 second, maybe even 10 seconds to do the process. But you imagine if Google took 10 seconds to respond every time you did a search, people would just go and find another search engine that was faster. So fast algorithms, really important for the person using it. But nevertheless, sorting is something that happens a lot. So here's my files sorted by date, sorted by size, so I can find the biggest ones. Here's a list of courses sorted by alphabetically, because it's just, if I put them up on a website, it's easier for people to find the right course number. My playlist, at this point, I sorted it by the longest song to the shortest one, but you could sort it alphabetically or by how many stars it's got or whatever you want to sort it by. So you've got some number or some value alphabetically that needs to be put into alphabetical order or numeric order. Down here, I'm trying to sort out a new TV for my in-laws who are moving at the moment. And so I sorted it by price because I know that my father-in-law won't want to spend too much money. And so this is from cheapest to largest, so cheapest to most expensive and so on. So sorting, it comes up all over the place. You'll spot it all sorts of places. Now, the algorithm that I like to start with is called selection sort. And again, we've got an interactive for that. And so here we've got boxes. Now, again, you could use scales. Remember that photo I had of the girl on the scales before? Much more fun if it's physical, but if you haven't got scales, you can just go to this on the field guide. Pick a couple of values and you find the largest value. Well, we just did the algorithm for that. Remember, find the largest value. So the arrow is pointing to the biggest one, so it's not that one. Try the next one. No, the orange one's bigger. Well, I may by chance have chosen the biggest one. So this website randomizes it every time, this web page. But I think I may have found the largest. Yep. What's the chances of that? Actually, the chances is 1 chance in 8 that the first one was. So I know that's the heaviest one of them all. And then we just do that again for the next one. So, that purple one's the heaviest so far. Oh no, that one's heavier. And so I'm comparing 2 at a time. So this is forcing me to do an if statement or a computational step comparison. And I think we're all convinced that that's the heaviest of what was left. So that's the second heaviest of the whole lot. So this is called selection sort. Select the heaviest, select the second heaviest, and so on. The analysis of it is, well, to find the heaviest out of 8, I'll let you type this in. I'll see who's awake. How many comparisons did I make to find the heaviest out of the original 8? Okay, Jennifer's going for 7. Anyone going to offer me something else? Yeah. So we did it before. Remember, if there are 8 items, it takes 7 comparisons to find the heaviest. But then I had 6. Yep. Then I had 7 left, which means I only needed 6 comparisons and so on. And yep, if you haven't carried out the algorithm correctly, and by the way, it's counting them down here, then it could get worse. But we're assuming it's done by a computer that it does exactly what it's told and gets it right. So, however, your mileage may vary. I see the look of experience there. Now, with selection sort, let's imagine that, say, we had n equals 10, that we're sorting 10 items. So the largest one will take 9 comparisons, then the next one 8, then 7, then 6, until you take 1 comparison. And there's a trick for adding up those numbers. And well, you could just put them in a spreadsheet and add them up, and that's absolutely fine. But most of your kids should be able to cope with this. You write the numbers down backwards, 1, 2, 3, 4, 5, 6, 7, 8, 9, and add all of these ones up, so which is going to be twice as big as we really want. Uh-huh. Yep, it's Gauss. Gauss's trick, it's called. And the and now if we add up each row, 9 plus 1 equals 10, 8 plus 2 equals 10, and so they all add up to 10. There are 9 rows, and each of them adds up to 10. So 9 times 10, but I have to divide by 2 because I've added everything twice, and so 45. Now, I've done that super fast. I'll let you unpack it if that didn't make sense. But basically, I have analyzed selection sort, and I'm saying selection sort on 10 items will take 45 comparisons. We have a program in the Computer Science Field Guide that you can download, and I know Jennifer's done a version of it on, I saw it somewhere, you can remind me where it is. But I can actually type in here the number 10, and so your students don't even need to, they can scroll back and see how the algorithm works, but that says generate 10 random values and sort them. And if I run it, it sorted 10 items, and surprise, surprise, it took 45 comparisons. We knew that, we analyzed it. And quicksort, which is a faster algorithm, I won't go into detail right now, it only took 21 comparisons. Is quicksort twice as good as selection sort? Good thought to put in your student's mind, because it's a trick question. It's not twice as good. We'll see later on. In terms of the time taken, that's another thing we worry about in terms of possible cost. They're all almost the same. No one's going to know the difference. It's so fast, no one will notice it. But if I make it 10 times as big, 100, they might predict the 45 will go up to 450. If you put it into, if you do that calculation I just did, it actually will be 4,950. So 10 times as many things does not take 10 times as long. It actually takes about 100 times as long. And that's a big deal. Selection sort is not a good algorithm because if you give it 10 times as much stuff, it takes roughly 100 times as long. And when multiplying by 10 gives you 100, that is the square of 10. And we'll see in a minute why that's the case. But basically, that's called an order n squared algorithm. It's roughly proportional to n squared. And in fact, if I go from 100 to 1,000, I'm estimating that instead of, well, that's just under 5,000 comparisons, it'll probably take 500,000 comparisons, right? Not 50,000, but 500,000. Let's run it. And sure enough, it's just under 500,000 comparisons. Quicksort, meanwhile, is only making 10,000. They're both achieving exactly the same thing. They both take 1,000 random values and put them into order. But one of them is saying, you know, if you're paying $1 per comparison, I think this might help your students to understand. This one takes just under $500,000 to do the job. And this one does exactly the same job for about $10,000. And if you're saying, look, if you were buying a house and someone said, I'll sell it to you for $500,000, and someone said, I'll sell you the identical house, no tricks, no hooks, it is absolutely identical, give me $10,800 and it's yours, there's just no comparison in, you know, where you would take it. Quicksort is astonishingly faster. So the bigger the N is getting, the more things we're sorting, the better quicksort is than selection sort. So it's not just that one's a little bit better, it's that one actually has a different complexity. It's behaving differently as it gets large. And we're starting to see that in the times. You know, quicksort 0.05 seconds, really fast, but selection sort 0.05, but quicksort many times faster. Okay. And just for fun, I'll put in 10,000 because at least on my computer, this time you really notice it. Okay. It's annoyingly slow. Sit here and wait for it. Sometimes I make students wait for these algorithms to appreciate what a slow one is. There we go. 49 million steps or 49 million comparisons, or 5 seconds. Quicksort did exactly the same thing with 157,000 comparisons and only a tiny fraction of a second. And now you know we can say, look, would you rather when you click on sort by date, it takes 0.02 seconds, which nobody can notice, or 5.3 seconds, which is enough time to get really annoyed and go and do something else and forget what you're even doing. And we're starting to see the fundamental difference between two algorithms that do the same thing but behave differently. And you can get students to do a graph of this. As that number increases, they'll see how, you know, one just goes up, well, it's n squared, It's a parabola if they've studied those, and the other one is almost linear but not quite. So I'll skip some of this because we can calculate it all. And there's Gauss's name, spelled with a double S for those who like it to be done properly. So in general, selection sort, you can calculate, if you do Gauss's formula correctly, it's n times n minus 1 divided by 2. We just put in the numbers 8, and 10 and 100 before. But if you write that out in full, it's n squared over 2 minus n over 2. Same value, right? Hopefully your students know what n squared is. If not, you may need to remind them. It's just n times n. But n times n gets really big. So if you have 1,000 items, then 1,000 squared divided by 2 minus 1,000 over 2 is, well, 500,000 minus 500, which is exactly what it did take. The thing is, this is the point where we go, who really cares about that 500, right? I'm going to sell you this for $500,000. Actually, no, it's really cool. You get a $500 discount. It's not that much. It's kind of interesting, but as the numbers get bigger, it becomes less important. If you put in n equals 1,000,000, that minus 1,000,000 over 2 is nothing compared with 1,000,000 squared over 2. Okay, and get them to play around with those big numbers. So in other words, what we say is that n squared over 2 is way more important than the n over 2. And so we're going to say it's order n squared, or big O of n squared. That's the important thing, as n gets really big. And that characterizes the algorithm. And when we see n squared, we go, that's not good, because if n is 10 times as big, n squared is 100 times as big. You get 10 times as many customers, it will take 100 times as long to process them. That is not sustainable. It's okay, might take a few seconds, whatever, but it really isn't ideal. Yep. Oh, thanks, Jennifer. The sort comparer. We can actually watch them run against each other. Nice. Okay. So lots of ways of comparing. Oh, in fact, that it might be similar to the one in the bottom right-hand corner, but there are. That's your one there, is it? That's cool. Okay. But definitely get them to work with really big numbers. Get them used to sorting 10,000 things. Even probably around 100,000, they'll find that selection sort just it's not worth waiting for. It probably takes half an hour. They might be bothered, they might not. Yeah. Okay. Oh, I see. It just works out the number of comparisons. Cool. That's fine. I think making them wait is also a good thing, but they once you get up to about, I think it's around 10,000 to 100,000, that's where they realize, okay, I'm going with quicksort. I can see that it's fundamentally better than selection sort. So that's enough for them to understand complexity, how bad one algorithm is compared with another. And the big O notation, why we only care about the n squared, not the n squared minus n. And a few other, and algorithms and problems, and that there's multiple algorithms for one problem. So that's all the basics of algorithms that they have. At which point I will bring in Jennifer's cheat sheet, which you just published a week ago, conveniently. Thank you for that. Which has some of the main speeds of them. So things we've looked at today, if we look at the logarithmic here, so binary search is the example, it takes log n time. And the curve for log n, so this is n getting bigger as we go across the graph. And students might think most things are linear, like this graph here, that as things get bigger, twice as big, it takes twice as long. But a logarithm, it gets twice as big, and no, it doesn't take much longer. And in fact, when things get really, really big, it still doesn't take much longer. And you try and feed a big, big, big input to a logarithmic algorithm, and it just won't take long. It's amazing. Unfortunately, for sorting, we know that there are no sorting algorithms better than n times log n. Now, that's actually quite a small, well-behaved number. So order n means it gets proportional to n. Remember, log n is a really small number, okay? No matter how big n is, log n is not going to be very big. So the curve for that is as n is getting bigger, it does go a little bit above a straight line, but the log n doesn't make a huge difference as n gets big. And that's quite a difficult concept for some students, I think. They think, oh, log n, it's unfamiliar, it's a big word, it must be a big number. It's not. Log n is your friend. Log n is cool. That's great when we get log n. And then quadratic or n squared. It's called quadratic because if you're dealing with quadratic squares, basically, quadratic just means squares. N by n is n squared, and so that does get quite bad. And we saw that with the performance before. But nevertheless, computer scientists still consider that kind of okay. It's going to finish in with while you're still alive, if not before you've had lunch. Where it gets really bad is what the standard calls non-polynomial time. It should really say exponential in the standard, but someone wrote non-polynomial and it stuck, and so we'll use that with our students. But it's exponential time, which means instead of n to the power of 2, it's 2 to the power of n, or 2 multiplied by itself n times. And that number gets really, really big, really, really quickly. And you can see the shape of this curve. The n goes up and it just goes through the roof. It takes a lot of time. And in fact, factorial is worse than polynomial. And a lot of algorithms students will look at are factorial. In fact, it's time for a factorial algorithm. So let's go to this is one of the interactives we built. Okay, and it's originally it was called the traveling salesman problem back in the day, but students will be more familiar with like couriers dropping off items, or maybe a rock band touring a whole lot of cities, or children being dropped off after a birthday party. Although someone did point out the algorithm for dropping kids off after the birthday party is you drop the most annoying one off first. But it's suppose you wanted to save fuel when you're dropping all these kids off a party, or you're dropping off courier, then here are 7 different places that we're doing the drop off. And we've got this program here, which will go through and try out every order that you could visit the houses that you're dropping the points off at. And on the right-hand side, it's recording the shortest route. Now, there's actually quite a few to try out. And in fact, it takes about half a minute for this to try out every possibility for dropping off at 7, say, a courier dropping off 7 parcels. That's not bad. It's worth waiting half a minute to save fuel when you're doing your drop-offs, right? You don't mind that too much. And on the right-hand side, after half a minute, we end up with the best solution. I then asked students, okay, that was for 7 drop-offs. It took half a minute. What if we had 14 drop-off points, twice as many drop-off points? And they would assume it's linear, probably a lot will. Yet they know it's a trick question, probably. But instead of half a minute, maybe they'll say, oh, it should take twice as long, twice as many drop-off points. And so it should take a minute. But actually, if I add that up to twice as many cities, down here it says it's going to take 9 years and 10 months. It's a factorial amount of time. It's order n factorial. Trying out every combination is factorial. And I usually make the point by starting that, and they can see it counting down from 9 years. And you can see that it's just a total waste of time if they're delivering things. Now, and that is exponential at work. So, the n squared we have with sorting, you're going to have to wait 2 minutes instead of waiting half a second. You can see why that's tractable. We call it tractable. It will finish, it will solve it, it'll just be annoying. But with this one, it's not tractable. In fact, the computer probably won't stay up for 9 years. There'll be a power failure, or it'll need replacing, or it'll get an upgrade or something within that 9 years. And, so it's just not tractable to make it run that amount of time. And then if we go to 3 times as big, then again, it's fun to get them to calculate it or work it out, but it's actually 3,800 million years. And I think that makes things a bit real, especially if you hit start. And it is counting down, but it's not going to finish in any of our lifetimes. And it's completely intractable. It's a complete waste of time even worrying about it doing this way. Now, at this point, we talk about, well, what if the computer was 1,000,000 times faster? Because computers are getting faster every year. 1,000,000 times faster, well, that would only take 3,800 years. Still a waste of time. And even if you had 1,000 computers all working on it at the same time, 1,000,000 times faster, 3.8 years. It's never going to work. And that's the thing about intractable is no matter how fast your computers are getting exponentially faster, but because the problem is exponential, it means every time a computer gets exponentially faster, we go, yay, we can do one more drop-off point. Instead of being limited to only doing 12, we can now do 13 in 10 years' time. And in another 10 years' time, we'll be able to work it out for 14. The algorithm is not feasible. Now, this is not the best algorithm for this problem. So remember, problems have algorithms. This is called a brute force algorithm. It's trying every possibility. And it you know, is not the best way of doing it. In fact, the best algorithm known for traveling salesperson problem at the moment is I think it's n squared times 2 to the n. So it's closer to 2 to the n than n factorial, but it's still exponential. And nobody knows an algorithm that isn't an exponential amount of time. Now, the really kind of curious thing about that is we haven't proved that you can't do a better one, but we don't seem to be able to find one. And there's $1 million prize for anyone who does find an algorithm that's better than exponential time, okay, that runs in polynomial time. Um, and in fact, the $1 million is nothing. You'd be so famous if you found an algorithm for doing that. And the other kind of curious thing is it's not just the traveling salesperson problem is just an easy one to explain to students, but there are literally hundreds of problems that we really care about like that. One is map coloring, which is just coloring in countries so that adjacent countries have different colors. And the question is, what's the minimum number of colors that I need? That's kind of not quite such a worrying question, but where it comes up is it's timetabling. If you're doing a timetable for a school and say, here are the subjects, you can put things beside each other or connect them up saying, look, the maths 1 class can't be taught at the same time as the maths 2 class because it's the same teacher, and maths 1 can't be taught at the same time as physics because students do both of those classes, but maths 1 for some reason could be done at the same time as English. They're not connected because there's nobody in common in these particular classes. Now, for a school, this diagram would be way, way bigger, of course. It's taking into account all the teachers and the classes and so on. But the question is, how do we allocate times to each of these classes so that no two adjacent classes have the same time? Can you see that that's identical to the map coloring problem, that no two adjacent maps have the same color, no two adjacent classes or connected classes are at the same time. And here it matters, what's the minimum number of times that we need to do a timetable for our school? Nobody knows how to solve that. And so what we do is we make do with approximate solutions. My problem here is still running, but I might just stop it now and go, look, I'll go with this solution. It looks good enough. Okay, I've run it for a few minutes. And if you put in some decent guesses at the start and so on, it probably will be good enough. I better stop it because it's actually warming up my computer because it's using power and so on. And so the thing is that there are all these problems we can convert to each other. Another one which gets a mention is the knapsack problem. I've got all these objects, like I've got a 12 kilogram, I can buy 12 kilogram objects that are worth $4. I can buy 1 kilogram objects worth $2 or sell them. What object shall I put in my knapsack or my backpack that I'm limited to 15 kilograms? Which one should I put in to be worth the most amount of money? Now, again, people aren't really worried about knapsacks, but they are worried about perhaps shipping containers and certainly buying shares and things like that. Like I've got this amount of money, these shares are going to this good, these shares are that good. What's the best mixture of shares that I could get to make the most of the money that I've got? And so variations of this problem come up all over the place. Nobody knows how to solve that problem optimally. Now, and so that is just a general problem. Another one is bin packing. We've got an interactive, here it is, where students can try this. So I've got some bins here, and I need to try and put these sort of lengths of things into it. Maybe I'll try putting big ones. Oh no, that one won't fit. I'll put it into the second bin. How many bins do I really need to be able to pack all of these? Like I've got a little bit of space left in this bin. So it's, maybe I can put the one with 3 in it, but I haven't got one of size 4, but maybe I should take out a bigger one and so on. Nobody knows the optimum way of loading that. So this could be loading shipping containers. It might be that I use 10 shipping containers where I could have got them into 9 shipping containers, or into 9 trucks or into 9 aeroplanes or whatever it is that I'm loading up. And nobody knows the best solution to that problem, or at least a solution that isn't exponential. Now, all of the problems I've shown you, and there are literally hundreds of them like this, are called NP-complete problems. They're a particular set of problems that are particularly useful to solve. Nobody knows a good solution for them. But the word complete means that if we did find a fast solution for any one of them, we can use it for all of them. So they're all intractable as far as we know at the moment. But if you found a fast bin packing algorithm, everyone knows how to adapt that for the traveling salesperson problem and for the knapsack problem and for the timetabling. Okay. Or if you solve the timetabling problem in a polynomial amount of time, we know how to generate uh, all the other ones in a polynomial amount of time. We just don't know how to do any of them. But if we can find one of them, we can do all of them. So no wonder there's $1 million prize, and no wonder you would be incredibly famous if you solved it. Might be interesting to know Sudoku was in that class, but Sudoku is intended to be time consuming, and just lots and lots of other problems in there. So, and it's very practical. So there's a company in Christchurch that has hired dozens of our engineers called Verizon Connect, used to be called Telagis. That's its office in Victoria Street. If you're in Christchurch, you can drive past it. They probably won't let you in unless you ask them nicely. And they solve that problem, but they cannot find the optimal solution. So they do it for trucks in America that are delivering Coca-Cola and car parts and all sorts of things. The person in America sends them a list of where they need to make deliveries. They send back a list of visit this place, then that place, and it saves fuel and time. They can't give them the optimum one. Nobody knows how to do the optimum one in a reasonable time, but they do make good guesses, and those guesses have a name. They're called a heuristic. So the word heuristic just means a rule of thumb, a rough approximation, something that's good enough. Okay. You may have heard it in interface design as well. We have heuristics for interface design. In that, we don't say you must always do this in an interface. We just say this is a good guideline in an interface. Maybe in some situations it's not a good idea, but it's probably a good thing to do. And it's the same with these heuristics. So the heuristics, one heuristic for this is just go to the nearest place and then the next nearest place to that and the nearest place to that. It's called the nearest neighbor algorithm. It works okay. It it can easily not give you the optimal route, and in fact, it can go quite badly wrong. But they are constantly trying out other heuristics to try and get good solutions. Their solutions are better than most other people in the world, so people use their algorithms and they pay them a little bit of money to save a lot of money on fuel. So it's a good feeling working for them because you're saving fuel, you're helping people to be more efficient, you're saving the planet, and you're being paid money. What more could you want? But I'm trying to get across, these algorithms are very real. They're actually used. They make a difference in the real world. The fact that it's not tractable is really, really significant. By the way, intractability is good if it's encryption. And so there are problems that we use in encryption, which we talked about recently, which are intractable. And that's good because it means people can't crack them. So actually, if you did solve the traveling salesperson problem, you would potentially wreck a bunch of algorithms. That's a whole interesting thing for your students to explore. So in general, if something is order n or n log n or log n or n squared or n cubed or even n to the power of 6, although really there are no algorithms that are n to the power of 6, but theoretically, we would say that's tractable. We can make it happen. If it's 2 to the power of n, 3 to the n, 4 to the n, or n to the n, no, that will blow up. And if you get your students to calculate a few of those numbers, they'll see how big they get very quickly. N to the n, by the way, is the same as n factorial. Okay, so it just really, really blows up. And there's, then, oh, by the way, if your students are interested in reading a bit more, there's a book called Computers Limited, which is about the limits on computers and what they can't do. And it's a layperson's explanation. It came from a radio show that a whole lot of talks that were given on the radio, so it's kind of a pretty approachable solution. By the way, we are dealing with big numbers. We've put calculators in this computer science field guide so that your students can say, oh, n is this much, and it's a n to the 6 algorithm or 2 to the n algorithm, and maybe I can operate a billion operations per second, and it will tell you how long that takes. So they can actually play with those big numbers. But quite often the answer will come up in centuries for how long it takes, or maybe tiny, tiny fraction of a second. So that, the only other thing I talked about, so that's exponential time. That's bad, but it can be computed theoretically, right? Then we have the whole issue of things that are not computable. And here comes Alan Turing. He worked this out in the 1940s, 1950s, that there are some things that a computer can never calculate. And one is the halting. I talked about tiling before. The halting problem is a big one. wouldn't it be nice if you had a computer program that you've typed and you feed it into the system and say, will this computer program ever finish, or will it be stuck in a loop? And the computer was able to tell you, oh, that one gets stuck in a loop, be careful. Nobody will ever write a computer program that can answer that question. It's an interesting mathematical proof. It's not very long, but it's a proof by contradiction. So your students might need to be a bit comfortable with maths to make sense of it. It's basically, if it was possible, then a strange contradiction arises. And tiling, here it is really simple. And I've done this. You just print out these tiles, dozens of them, and you say, with these tiles, can I use it to tile an arbitrary size room? The rule is, of course, that red has to match to red, purple to purple, and so on. Simple rules, simple problem. Nobody will ever write a program that can tell you that you can tile an arbitrary sized room with those tiles. You think surely a computer could work that out. Never. Okay. And sometimes this also, I think, helps students get their head around things like AI, which is just a program running on a computer. It will never be able to do that, okay, because it is a program running on a computer. And Turing knew that decades ago. Some of these things may change a little bit if quantum computing becomes a thing, but what's been done in quantum computing so far doesn't look like it will. But in the standard, students are expected to talk a little about the future and societal issues and things like that. And certainly for excellence, they should probably explore quantum computing and what the limits of it are and how it might change some of these absolutes that I've been talking about. Right, there you go. 30 hours of material in 1 hour. How many people have we still got on the call? Oh, everyone's there. Well done.
Oh, Tim, you're amazing.
I
Thank
will
you.
stop.
I'm just going to stop recording there, and then, oh, sorry, have you got more?
No, no.
Yeah.
Oh, no. I'll just put up that last slide if anyone wants to refer to it. It's something I wrote a while ago, which is, don't bother reading it now, but it's kind of a one-page summary of everything I just said, which I think might make sense to students after they've studied it. It probably will just look like a whole lot of words before they study this stuff. But if everything there does make sense to them, then they've probably understood to a merit nearly excellence level if they really can dig down and explain all of those things. Yeah. Cool. Stop sharing.
Thanks, Tim. I'll just stop recording.